Hi, this is the second video on the central limit theorem for ergodic averages for sampling algorithms targeting heavy tail distributions. And in this video, I will discuss the unbiased sampling algorithms. Okay, so this is joint work with Miha, Brešar, and Gareth. Okay, so we start with a pi that has polynomial tails on RD, and the problem is to compute an integral of this type. First, one uses a sampling algorithm, which is a chain, and then the ergodic average of this chain will converge to pi. And what one wants to know about is the error, right? So what is the confidence? The confidence interval finite from this thing, and what is the rate of convergence of x to the stationary metric pi? And the answer, as discussed in the first part of this presentation, lies in this L drift condition. Okay, so we take a Laplace function that goes to infinity at infinity, and then we need to study the excursions of the process. We have two functions, var phi, psi, that do that for us, right? So var phi is a positive function that tells me, if I look at the process 1 over v of x, how much I need to subtract from the process to make it super martingale. Okay, so clearly I need to subtract something, because if I didn't subtract anything, this would be a post-Laplace drift condition for x to be transient, because 1 over v is a bounded function. Okay, so in fact, this var phi needs to satisfy this sort of limiting behavior as r goes to infinity. So var phi will start at 0, and then it needs to increase from 0 as fast as it can to subtract as much as I can to make it come back to the compact set as fast as possible. Okay. So, but you can't subtract too much, because r times var phi 1 over r needs to go to 0. So this needs to be sublinear at 0. So it's sort of convex at 0. Now, the function psi really controls the exit probability at a high level. So how fast I go into the tails, right? So really, this good, well-chosen psi will be equal to 1 over this probability as r goes to plus infinity. Okay, let's now go and see how that does with the algorithm. Okay, what these conditions do for you with the algorithms. We'll consider finite variance random walk metropolis, infinite variance proposal random walk metropolis, Mala, Ula we've already seen in the first presentation, stereographic projection sampling. And at the end of the presentation, I will also draw some comparisons with the independent sampling. Okay, so this is the unbounded, unbiased dynamics, right? I start with arbitrary dynamics Q, and then I accept the move from Q with this probability, and the kernel of X is then given by this, which R of X is the probability of not moving. Okay, and such X will have pi stationary measure. And we're really looking at polynomial pi. Now, see, the thing to sort of bear in mind is that really this pi decays polynomially, and it has two parameters, right? Pi is in d-dimensional space, and the tail doesn't depend on the dimension, but they're sort of like independent parameters, as you will see, right? But the tail decay is v. Okay, the thickness of the tail is v, and v can be arbitrarily small. Now, how does finite variance random walk metropolis work? Well, it proposes from some distribution. I wrote here normal, but I could have written any distribution here for this analysis that has second mode. And I would get so the same conclusions. And I accept with this alpha from the previous slide. Now, because this Q is reversible, only the quotient of the proposal and point where I am, pi value proposal point where I am, that sort of matters. And now I go and I find these my drift conditions as well. I look at the transition kernel. This transition kernel gives me this var phi psi. And now you see these are polynomials, okay, and neither of them. This var phi depends on the thickness of the tail. This guy doesn't depend on the thickness of the tail, but neither depends on dimension. And as a result, from our theory, when we applied, when I look at a function g that grows at least as fast as x to the s for 2s smaller than me, 2s needs to be smaller than me, so that this polynomial is in the L2 of pi. Okay? And then if this 2s is smaller than v, but greater than v minus 2, then the CLT will simply fail. And if G is bounded, so estimating some probability of some event, then if I don't have two moments, then the CLT will fail. And similarly to the ULA in the first presentation, here we also get lower bounds. Okay, we get lower bounds on the total variation of the Wasserstein distance. If I take here p equal to 0, then I get a total variation here, and I get that the rate is n to the minus v over 2. Upper bound rate, of course, is known from the classical upper bound drift condition, and it's exactly upper bound is also n to the minus v over 2. Okay? And so the thing to note here is that really the failure of the CLT for bounded estimators is equivalent to the distance from the stationary measure decaying in a non-summable way, you see, because this will be non-summable when v over 2 is smaller than 1, right? And this is exactly the condition for the CLT to fail. This is somehow a meta theorem that will sort of arise, meta statement will arise in all the examples when we apply our theorem. Okay. Another thing to notice here is that you see here the failure of the CLT does not depend on the dimension. It only depends on the thickness of the tail of pi. Okay. And you see if I take b equal to 1, then this is one variation here, and this will have exactly the same rate as the Wasserstein 1, L1 Wasserstein, right? The upper bounds, as I say, the upper bounds are known from the classical theory. And also here in this bit, I only talk about the failure because that's new. The sufficient conditions tell me that if 2s is smaller than v minus 2, then I will have CLT will hold. Okay? Likewise here. Okay, so let's look at some pictures, right? So we try these tails, and we want to now compute the estimator for the norm of x, right? And we take a v which is has 3 moments, and if v has 3 moments, v minus 2 is really 1, and that's less than 2s, right? It's less than 2s, which is s is 1 here, so 2s. So by our theorem, the CLT should fail, and this Q2 plot sort of corroborates that. Okay. Now, a way that one can modify a random walk metropolis is to take an infinite variance proposal. Okay, so we take a proposal which is of t distribution type with eta moments. Okay. So this is the proposal, and then we just do the analysis. We look at this one-step kernel, compute the function y5, compute the function psi, and we get here. You see again two polynomials, and it turns out that our theory from video 1 really tells us that, you see, again, there will be a failure of CLT, but a much narrower interval, right? The interval where it fails is that when v minus eta to v, right? But I can take eta close to 0, so it will fail only for very few functions. Likewise, it will hold the CLT for bound functions, will hold for much heavier, anything that is heavier than eta. For this algorithm, if tail decays slower than eta, right? Or sorry, faster than eta, then I will have the CLT will fail, will hold. Now, here the rate of convergence is also improved. It's analogous. You see the total variation, guys. When I take p equal to 0, I get n to the minus v over eta. Okay. And the upper bound in this case is also known, and this is exactly the rate. And again, this idea that I was trying to explain earlier, where I look at the summability of this. So if this is not summable, okay, this means that v over eta, total variation is not summable, this v over eta is smaller than 1. Okay, this is exactly the condition for the failure of the CLT for bounded estimate. And of course, there is this matching between the total variation and the Wasserstein distance, upper bounds at 9. Okay, and the sufficient conditions for the CLT also kick in from the classical theory. Okay, so these are really sharp, are necessary conditions that are actually sharp. Okay, now you see, this guy behaves better, right, than the thin tail guy. So why is that? So we have this polynomial pi. We have the acceptance probability, which is of asymptotically of this type. you see. And finite variance sampler will have this var phi, this return time, is going to be 1 over r to the 3. While here, this guy will return at a, you see, this guy grows much faster from 0. Var phi grows much faster. I'm subtracting much more at 0. So it is, I need to subtract more for it to be a supermarket. Okay, so this is the first drift condition in my L drift conditions. Okay, so why does this work like that? Why does the heavy tail guy do this good job? You see, if I'm far in the tail, and if I am far in the tail, and if I propose a good heavy tail move, which takes me close to the origin, this quotient will asymptotically be greater than 1. So I will accept it. So I will move fast back. Okay, while the guy with second moment proposals will never make such moves. So it will move backwards slowly. So it will come back from the tails in a very slow fashion. You see, that's coming back is really helped by the heavy tail proposals. But going out is not. And the reason for this is because the uh, acceptance probability will slow me down. You see, if I'm somewhere in the bulk and I propose a heavy tail move outwards, then this acceptance ratio will be tiny. You see, and furthermore, you see here that this acceptance ratio depends on the heaviness of the tail. You see, it depends on the heaviness of the tail. You remember, I want this psi to grow as slowly as it can. And the growth rate of this psi, of course, is given by v plus 2 or v plus eta here, right? And this, if v is big, then this doesn't make much of a difference. It makes more of a difference when the tails of pi are really, really very thick. So in other words, when v is very, very small. But nevertheless, these two algorithms behave in the same way as going out. They go out, they diffuse outwards, even though the second one has heavy tail proposals. Right. So what I was trying to explain, and the duration is these. If I make a big move towards the origin, it's automatically accepted. That's why this algorithm works much faster. Okay, now we can see that this sort of works here. These QQ plots for this is 20-dimensional situation. I the look at the event that norm x is greater than 5, and you see that if I have um, um, the uh, finite variance guy, okay, finite variance guy, then not with the Gaussian, even T3, right? So it's got 3 moments only, but nevertheless, it's still going to fail. While the guy that has very few moments, the CLT will hold in this 20-dimensional example. Okay. Now, let's look at the next algorithm. Okay, look at Mala. So Mala is based on the Langevin diffusion, which has stationary measure pi, and then the proposal for Mala is given by the Ula kernel. Okay, the Ula kernel we discussed earlier, and then we do the accept reject on that. And it turns out that for the polynomial pi, polynomially decaying pi, the L drift conditions, they look, these functions var phi and psi, they look exactly the same as for ULA and exactly the same as for the finite variance random walk. Okay. And because this is the case, the theorem will look exactly the same. Okay, so Mala will fail, the CLT will fail if the growth rate 2s is between v minus 2 and v, and it will fail for bounded guys if the tail doesn't have second moment pi. Okay, why doesn't have a second moment? Again, importantly, exactly unsurprisingly, these functions don't depend on the dimension. Of course, these results will not depend on dimension, only depend on the thickness of the tail. Okay. And rates of convergence are exactly the same as for the random walk metropolis with finite variance or for ULA, nothing changed, right? So, yes, okay. So here are some examples for the comparison between random walk metropolis and Mala, just to show that in practice, they also fail, right? They also fail at the same, for the same kind of, for the same function. And the pi that has only 3 moments. The pi that has only 3 moments. Right. Gradient really doesn't help. This is not a surprise, even though so the results previously at the first proved this, in the sense that, course, the gradient will be vanishing on you, right? The gradient in the drift is 1 over norm x, size constant over norm x. And then so this gradient doesn't do much job, right? Ula and Mala also, there is no difference. The failure happens in the same way. And Mala behaves like Ula because of this vanishing gradient, because of the polynomial nature of pi, the acceptance ratio really goes to 1 when x goes to infinity. That's how these things are proved. You prove the result for Ula, and then you deduce the result for Mala, or var times I find from Mala, by really considering, showing that the acceptance ratio goes to 1 as x goes to infinity. Okay. So now another recent algorithm that is interesting to study in this context is the stereographic projection sound. Okay, so what does this guy do? I think pictures the 1,000 words here, right? So this line here is my RD. Okay, and then I will wrap this RD onto the sphere. So I take a point in RD and I connect it with the line, the north pole of the sphere that sits in D plus 1 dimensional space. Okay, there's a unique point. I map this point here. You can see that if I go out to infinities on both sides, this will be mapped under the stereographic projections into a cap around the north pole. And of course, this bit will be mapped onto the hemisphere below. So that's the stereographic projection, classical object, okay? And now the idea is to sort of take a distribution of my RD and just pull it back onto the sphere and do the random walk metropolis on the sphere, okay? So how will this random walk metropolis on the sphere work? Well, if I'm at some point in the sphere, I will look at the tangent space. Actually, you just want to make some Brownian increments, right? But the way to implement Brown increments most easily, maybe, or this is how in this paper they did it, right? So is to take a tangent, draw normally on the tangent, and then just normalize onto the sphere. You see, if you're at this point, you draw normal from this tangent space, and then wherever you get, you then just project it down onto the sphere by normalizing you see that means that you can move in principle, proposal moves in principle anywhere onto the hemisphere, sort of defined by the point where you are. Okay? This can happen. And now the algorithm looks like this. Okay, so the formulae are not so important. The details of the formula are not important. The acceptance probability is important. Okay, the acceptance probability is not going to be what I sort of propose using that sort of normal move and projection onto the sphere over where I am, but there is this additional quotient that comes out of the Jacobian of the stereographic projection. And in this paper by Young, Matuszynski, and Roberts, what they do is they study pies that don't have tails that are too heavy. Okay, so this pi of x is x squared. Pi of x times x norm x to 2d is bounded on the entire RDC. This makes the algorithm ergodic and makes the CLT hold for all them two functions. But if I don't have d moments, then this condition will not be satisfied, and they don't say anything about that case, right? So you see, think about it, right? So you have if d is 100, right? So if you don't have 100 moments, if you have 100 moments, then the algorithm will work wonderfully. But if you don't have 100 moments, then it's really a question what happens. Okay? So and really, when this condition is violated, when the condition in the paper that I mentioned earlier is violated, what this really does is in the picture of the density on the sphere, it makes the density of the sphere unbounded at the North Pole. You see, the case that was studied in that paper was the density is bounded. Okay, the density is nicely bounded on the sphere, and you have sort of these Brownian moves. Of course, it is expected to get uniform ergodicity in the algorithm to behave in a very stable way. But when it's unbounded, what happens? And this happens exactly when the tail behavior, the pipe doesn't have D moments. Okay? As I said, when D is large, this is often happens in upper. Okay. Now, we study upper bounds and lower bounds because this part has never been studied. Okay, so for the upper bounds, we need to use the classical drift condition for the upper bounds, right? So this var phi, this phi is sort of concave function and tells me how much can I add to the process while it remains for it to remain still supermarket, this quantifies the rate of convergence and the CLT and things like that, given sufficient conditions. And it turns out, in this case, if you look at this kernel, you can see that phi is of this type, it's r to its power, and the Lyapunov function is norm x to the 2 gamma, so it's stretched, sort of, it's norm to some power, right? And gamma really needs to be close to d over 2. And see, if gamma is d over 2, then this power here really becomes v over d. And this is good because in this case, you need this concavity of this phi, right? So v over d is really smaller than 1, so this will be concave. Okay. And for our own drift conditions, we find this function var phi and psi exactly as before, right? We just look at this one-step transition kernel. This is crucial, right? I mean, these conditions are no harder to apply than these conditions, okay? In some sense, they're easier because this function is really looking at the process 1 over v of x. 1 over v of x is a bounded function, it's a bounded process. While here, of course, it is not because v is non-bounded. Okay. So here you see interesting things start to happen because this starts depending on d. You see, this is very different from the previous algorithms. There was no dependence on d in this situation. And this means that in the result, I will see the dimension. Okay. So I take this heavy-tailed guy. I take, it has v moments. And our theorem now gives us both sufficient and necessary conditions, right? The sufficient conditions are from the classical theory, and the necessary conditions are from Eldridge conditions. Okay. So you see, if I take this polynomial, right, that may have a CLT, it will have it if this 2s is smaller than v minus d over 2. Okay, so you see, the thickness of the tail is now related to the related dimension of the space. And if it is not, if it's growing faster than v minus d over 2, then there will be no CLT. Likewise, for a bounded function, you see, if I have v, which is greater than d over 2, then the CLT will hold. And if the tail is very thick, thicker than half the dimension of the space, then the estimators for events will not have CLT. Likewise, we get lower and upper bounds, matching lower and upper bounds and total variation and Wasserstein distance. Okay, again, I'd like to take p equal to 0 here, but think about maybe this is total variation, you see, and you see here the rate. You see the rate is going to be v over d minus v. And you see this funny thing that I was talking about earlier about the summability of this guy really matching if it is not summable, then I get a failure, right? So this is not summable, v over d minus v is smaller than 1, okay? And this is exactly this condition. So it's exactly the failure of the CLT. Of course, Wasserstein distance, we can also do that, right? Now, what happens with the sampler, right? Well, let's try to understand the dynamics. So the thing is here, you see, this psi actually works much better than in these classical samplers, random walk metropolis and Mala sampler. Because what happens is that this exit probability, which is sort of given by 1 over psi sort of mimics this exit probability. This is asymptotically equal to the one jump exit, okay? So this is to do with the fact that density is unbounded at the North Pole, and the proposal can take you to the North Pole in one jump, in one step. Okay, so this is what happens here, and this is very different from. So you will go out into the pole very, very quickly. Very different, even from the infinite variance random walk metropolis, where the accept reject ratio was sort of slowing you down when you're going out diffusely. Okay. However, once you're in the tail, okay, so of course, if my tail is sufficiently thin, so if it's thinner than it has d moments, more than d moments, then I have no problem. But if I have less than d moments, okay, if I have less than d moments, fewer than d moments, then I have this density, this infinite there, and anything I propose to go back, the stiffness ratio will really slow me down. Okay, so what this means is that in this case, this guy independence, classical random metropolis with infinite variance proposals would outperform SPS. Okay. So this SPS goes out fast, but then it's stuck near the North Pole. It takes the ages to come back because the accept reject even if I propose going downwards, exactly check to slow me down, while this infinite variance random walk metropolis will sort of diffuse out and then come back fast, in particular. And you can see here, for example, so this is two plots for SPS in dimension 1 and in dimension 4. Okay, we estimate this event. Okay, we want the probability of this event, the x, norm x greater. And in dimension 1, okay, in dimension 1, you have, you see, 1 over 2, I have 1 half of the dimension because this V has one moment, okay? So the CLT should hold, you see, and it holds. And if I take a four-dimensional example, okay, then D over 2 is 4 over 2 is 2, and that's greater than 1, the CLT actually fails. So this is not a good situation because you need to somehow, it is the interplay between the thickness of the tail and dimension that tells you how whether this is going to work or whether it's going to crash. So here is a table that summarizes all these findings for the algorithms that we've looked at, right? So you see here in the first column, we simply say when the CLT will hold for an estimator of an event. Okay, so for the finite variance random walk metropolis, it will hold if I have at least two moments. If I have infinite variance random walk metropolis with proposals with heaviness of tail decay eta, then if V has more moments than eta, it will hold. Right? So you see, I can take eta small, and then this will hold. Ula mala behaves exactly the same as this. Well, SPS, in the situation when it is not uniformly ergodic, in other words, when the tail is thicker, it doesn't have distribution, doesn't have D moments, then it will simply fail quite quickly. If D is large, it will fail at half over D, right? So it will hold when if V is in this interval between D over 2 and D. Now, this rho here is the rate of decay of these in total variation. Okay, rate of decay in total variation. You see, it's always the thickness of the tail divided by some factor. Okay, and of course, when eta is small, I can make this guy go very fast. But here, and these first three classical algorithms, their rate of convergence does not depend on dimension. While here, of course, it depends on dimension, and it can be quite bad. So now the question is, what are these factors that I'm dividing by? See, these are these numbers here. So if I go look here, this is exactly the stuff that I was talking about at the beginning of this video, right? How slowly does the function r bar phi of 1 over r converge to 0? Okay. And this beta really tells me this. And you see, these beta factors are really 1 sin of var phi. So how fast does var phi go up from 0? This doesn't depend on dimension, while in the SPS case, it will depend on dimension. So, and then this jump really describes how I go into the tail, right? This is all about how I return from the tail, how I go into the tail. And these algorithms are such that I will go into the tail slowly. I will diffuse, even if I have heavy tails in infinite variance random metropolis, while this SPS will jump into the tail in one step, but then will get stuck. And this situation is really analogous to this independent sampler. Okay, independent sampler is a silly algorithm that just samples from the same distribution, not taking into account where I am in the state space. And Mangers and Tweedy a long, long time ago already worked out that if the proposal distribution is thicker than the target, then this independent sampler is uniformly ergodic. This is much like the SPS case. Okay. However, if it is not thicker, if it's thinner than the target, then I will lose the CLT. I will lose the CLT if it is smaller than k over 2, or if k over 2 is smaller than the is larger than if k over 2 is larger than v. Right? And this independent sampler has a similar sort of behavior as as SPS in the sense that it goes out into the tail in a single jump, but then it gets stuck in the tail, and the return time is very slow, and that accounts for the slow behavior of the thing. If I don't have the if I don't tune it correctly, right? So what I want to do is I want to choose k. See, I want this beta to be as small as possible. I want to choose k as close to b as I can. See, in this algorithm, I can't do that. Well, I could try to, because my v is given, my d is given. There's no freedom right here. At least I can choose the proposal distribution, right? So if I choose it, and if I could hit v, then I would have the best possible algorithm asymptotically, right? But of course, this is impossible to do in practice, right? So you see, these L-drift conditions, they're conditions for general chains, right? You don't need to know pi ahead of time. But of course, we're studying algorithms in this video, right? So we have a phi that's fixed. We have a pi that's fixed. We're hitting this pi. And if you've chosen this L-drift condition sensibly, they're sort of asymptotically optimal, then it turns out from the theory that this tail of pi needs to be given in terms of these functions bar phi and psi. You see, this means these functions bar phi and psi are really one function because they're sort of expressible in terms of the tail. Okay, and you can see that in our condition for the CLT to hold, right? So I take a kernel P, and the CLT will hold for sort of a bounded estimator if this function where G1 is really the inverse, G1 inverse is the inverse of G1, which is given 1 over R phi 1 of R, okay? If this is integrable. But using this relationship, you see, this sort of reduces, I can forget about var phi, I can write about psi and write everything in terms of this inverse of this function, which is given in terms of phi, var phi, okay? And now, if I want this to hold, what I want is for this function to grow as fast as it can, okay? To go to infinity as fast as it can to make this as integral as possible. So this one needs to go to infinity as fast as it can. So this means that its inverse, G1, needs to go to infinity as slowly as possible. And if it goes to infinity as slowly as possible, this means that this guy needs to go to 0 as slowly as possible. And this is equivalent to the function phi of r growing as fast as I can from 0. Right? And this is exactly the intuition from the beginning of the video, where you see I need to subtract as much as possible to be as far away from transients as I can. So this is a probabilistic tutorial. Okay, so the conclusions, we've got these algorithms that can things can fail, right? So the CLT can fail. Okay, so one has to be careful. Bar phi tells me how sticky this thing is, how long it takes me to come back. Psi tells me how long it takes me to go into the tails. Okay, these functions are given in terms of the one-step transition kernel. Okay, and in this situation, when you have very heavy tails, of course, the best thing that we've seen in this class was the heavy tail proposal random walk metropolis. But if you have polynomial tails, but you have d moments, then SPS sort of performs best. Okay. So you see, you want to have something that the best possible sampler will have this psi that grows slowly at infinity, because that will mean it goes to the tail as much as it can, and it will be var phi fast in the sense that var phi will grow out of 0 as fast as it can be. So I'm subtracting more to be far away from it. And right, we have a new sampler in mind for this that satisfies this and definitely beats everything in CMALG as well as Hamiltonian Monte Carlo, but this will be a topic of another video. So here are the references. Thank you very much for watching.